Have you ever wondered what you're made of, or how big the universe is? Today we'll look at the very small and the very big. We're talking elementary particles and cosmology. To start, let's look at the bits and pieces that make up everything we know. You've probably heard of protons, neutrons, and electrons. For a long time, these are the smallest building blocks we knew existed. Combinations of these three particles form the elements on the periodic table. Positively charged protons and neutral neutrons, classified as baryons, form the nucleus of an atom. Negatively charged electrons, classified as leptons, move around this nucleus. Protons and neutrons have internal structure and are more massive than electrons, with a mass of 1.67 times 10 to the negative 27th kilograms. Because of their small size relative to their mass, nuclear matter has a density of about 10 to the 17th kilograms per meters cubed. This material is extremely dense, about 10 to the 14th times the density of water. A portion of this nuclear material about the size of a penny would weigh nearly 30 million tons. Electrons, however, lack internal structure and have a mass of only 9.11 times 10 to the negative 31st kilograms. You might be wondering how protons and neutrons stay together to maintain a nucleus, since like charges repel, as dictated by the Coulomb force. A special force called the strong nuclear force counteracts the effects of Coulombic repulsion, helping protons stay with protons stay with neutrons, and neutrons stay with neutrons. But more on that later. Let's talk stability. Not every nucleus has the same amount of stability. Some are more stable or less stable than others. But why, and what does it mean to be stable? When protons and neutrons come together to form a nucleus, some of the total mass is released as energy, which we call binding energy. To find the binding energy per nucleon, we just divide this energy by the number of nucleons. Of all the elements, iron has the most stable nucleus. Everything above and below iron on the periodic table wants to become more stable. For elements below iron, this means fusion, and for elements above iron, this means fission. So what does that mean? Fusion is the combining of atomic nuclei, while fission is the splitting. Fusion can be observed naturally in stars, which fuse hydrogen atoms into helium via a process called the proton-proton cycle. Stars bigger than our own take this process even further and can fuse up to iron via the triple alpha process. Once iron begins fusing, this process is too energy-consuming for the star, and it dies in a brilliant explosion called a supernova. Fusion and fission are types of radioactivity. Radioactivity is when unstable nuclei decay in an attempt to become more stable, releasing energy and/or charged particles. There are three types of radioactivity: alpha, beta, and gamma decay. Alpha decay is the release of helium nuclei, such as the decay of radium-226 to radon-222. Beta decay can be broken into three subcategories. Beta-negative decay results in the release of an electron, an antineutrino, and energy. Beta-positive decay releases a positron, a neutrino, and energy. Electron capture releases just a neutrino and some energy. Gamma decay is the release of gamma photons, which, remembering the electromagnetic spectrum, are very high-energy electromagnetic radiation. All of these types of decay are balanced through a variety of conservation statements based on several principles of physics and chemistry. Mass and energy, charge, baryon number, and lepton number are all conserved. What do I mean when I say baryon or lepton? Well, scientists have discovered that protons and neutrons are made of even smaller pieces, called quarks. Electrons, with their small mass, are leptons, and we classify them as elementary particles. Baryons are particles with high mass, like nucleons. Particles that fall in the middle are called mesons. We can group baryons and mesons together into what we call hadrons. Scientists currently use the Standard Model to represent and describe these tiny building blocks. It contains charged quarks, up, down, charm, strange, top, bottom, charged leptons, electron, muon, tau, and uncharged leptons, the electron neutrino, muon neutrino, and tau neutrino. Protons consist of two up quarks and a down quark, giving them their overall positive charge. Neutrons are composed of one up and two down quarks, giving them their neutral charge. So, how do baryons, mesons, and leptons interact to form particles like protons and neutrons, or create atoms? Hadrons and leptons interact through four forces, each with a different strength, range, and exchanged particle, called a gauge boson. To better understand gauge bosons, picture two particles tossing a ball back and forth between each other. What are these four forces? Well, because these particles have mass, gravity acts on them. Gravity is the weakest of the four forces but has an infinite range, as we can see in the gravity force equation. Its exchange particle is called a graviton, but scientists have no concrete proof of its existence, and it presents a huge mathematical problem in general relativity. Any charged hadron or lepton is acted upon by the electromagnetic force. Like gravity, it has an infinite range, and it is the second strongest. Its exchange particle is called a virtual photon. Now we have the two nuclear forces. The first is the weak nuclear force. Like its name implies, it is a very weak force, second only to gravity. It acts on leptons, with weak bosons as its exchange particle. It can act over a range of about 10 to the negative 18th meters. The other is the strong nuclear force. It is the strongest of the four forces, acting on hadrons and quarks. It has a smaller range of 10 to the negative 15th meters, and its exchange particle is called a gluon. Gluons are shared between quarks, acting as a glue, keeping them together to form hadrons. The existence of these four forces is heavily agreed upon by scientists. However, unifying the four of them in one coherent theory is no laughing matter. The current theory, called the Grand Unified Theory, unifies all but gravity, but scientists are constantly in pursuit of a theory of everything that unifies all four forces. Now that we've talked really small, let's talk really big, the universe. There are so many questions about the universe that we live in, and it's a really big topic with lots of ideas to explore. Where and when did things begin? The universe is an estimated 13.8 billion years old. It began with an event that we call the Big Bang. Since the birth of the universe, it has been expanding at an increasing rate. The current diameter of the universe is thought to be 93 billion light years. How do we know how old the universe is? Well, when electrons join nucleons to form atoms, energy in the form of photons was released freely. We observe these time-stamped photons today, and collectively these photons are called the cosmic microwave background. The existence of the cosmic microwave background tells us information about the age and composition of our universe. While we have information about the age of the universe, the cosmic microwave background, and expansion, we also have a lot of unanswered questions concerning phenomena we observe but have difficulty explaining and understanding using classical ideas of matter and energy. Measurements and calculations concerning the universe indicate that we calculate more mass than we observe. Where is all of this mass, and what is it? Scientists call it dark matter, a sort of antimatter that doesn't emit light. This idea is supported by gravitational lensing, where matter from one galaxy distorts light from another. When the bend of this light is more severe than the observed mass accounts for, scientists turn to dark matter. Current estimates of the universe's composition indicate that it is 22% dark matter, in contrast with just 4% regular matter. What is making the universe expand? What is the other 76% of the universe? Scientists call it dark energy and believe it to be a kind of anti-gravity force that pushes objects outward rather than pulling them inward. Scientists still have many questions about the universe, but they learn new information every day. As time goes on and technology improves, who knows what we might discover about the world we live in? From the very tiny to the very large, there is so much left to learn. And who knows, maybe you'll be the one to identify the particles that make up dark matter, or the one to establish a theory of everything. For now, keep exploring and let your curiosity guide you. You never know what you might find.